In an electron microscope, the resolution that can be achieved is of the order of the wavelength of the electrons used. In order to resolve a width of 7.5 into 10 raised to minus 12 meters, the minimum electron energy required is close to what? Okay, so herein, let's understand this question. There is an electron microscope that is being used to resolve objects, that is to observe objects basically. Okay, so the observation of the objects happens because the electrons are going to interact with the objects, and the reflected electrons or the refracted or diffracted electrons are going to be seen by us. That is why the observation happens. Okay, so this is the order of the width that we want to resolve. So it is understood from the language of the question that the wavelength of the electrons used is going to be in the same order as that of the width. So herein we can understand that lambda is going to be equal to, or rather in the order of 7.5 into 10 raised to minus 12 meters. Okay, and the energy of the electrons has been asked. Now electrons here are to be treated like particles. Everything in nature is a wave particle, but herein in this particular question it is important to understand from the statement that electrons are to be treated like particles. So energy of a particle is going to be given as p square upon 2m. If it was a massless particle like a photon, which is to be treated like a wave, then the energy is going to be hc upon lambda. Okay, so here by the de Broglie equivalence, okay, we get this is h upon lambda the whole square, because lambda for matter particles is going to be h upon p. So p is going to be h upon lambda whole divided by 2m. We are supposed to know the mass of the electron. The Planck's constant is 6.63 into 10 raised to minus 34 joule second, and the wavelength we can substitute as 7.5 into 10 raised to minus 12 meters. So herein we'll get the value of the energy in joules. So we get 6.63 into 10 raised to minus 34 joule second divided by 7.5 into 10 raised to minus 12. So the whole thing over here is going to get squared. Okay, so this is 1 over 2m, so this is 2 into 9.1 into 10 raised to minus 31 kg. Now it is better to calculate in the last step, and we know that there is going to be one more step involved, because everywhere the energy has been given in kilo electron volts. So we know that we anyway have to convert this energy that we have obtained in joules into kilo electron volts. So it does make sense to multiply over here itself with 1 upon 1.6 into 10 raised to minus 19. Okay, so this will give me energy in electron volts. Okay, that we can separate out by separating out 10 raised to 3 and write the energy in kilo electron volts later as we proceed with the calculation. Now this much is like the physics part of this particular question ends over here by writing down this equation. Now we need to understand how to approximate this value to one of the options in a fast and efficient manner. So for that we understand what is happening with the powers of 10. So let's analyze only the powers of 10 and write down everything else separately. So this is 6.63 into 6.63, and in the denominator, okay, in the denominator we are going to have 7.5 square. So if anything is ending with 5, it is usually very easy to square that thing. So 7.5 square is going to be equal to 7 8s are 56. So this is going to be equal to 56.25 into 10 raised to minus 24, because 10 raised to minus 12 square is 10 raised to minus 24. And here I'll choose to write down minus 34, 10 raised to minus 34 twice like this. Okay, then I have got the mass of the electron, which is 2 into 9.1 into 10 raised to minus 31. Okay, and I have got another term 1.6 into 10 raised to minus 19. Now what I choose to do is cancel out the exponents so that I get a simplified, relatively simplified expression. So 10 raised to minus 34 goes like this, and here we are left with 10 raised to minus 3. 10 raised to minus 34 over here will go with this 10 raised to minus 24, and here we are left with 10 raised to minus 10. So both these will go with 10 raised to minus 19, and here we will be left with 10 raised to minus 6, which on taking in the numerator becomes 10 raised to 6, which I have to separately write as 10 raised to 3 into 10 raised to 3. Why do we do this? Because we want the answer in kilo electron volts. So I absorb this 10 raised to 3 in kilo, and now I am left with into 10 raised to 3 kilo electron volts is the answer. So now once the exponents are taken care of, all I am left with is to find out the answer of the significant figures. Alright, so we have the calculation as 6.63 into 6.63 into 10 raised to 3 divided by 56.25 into 2 into 9.1 into 1.6. This is what we are left with. Now here is where our agility of mathematics and our smartness in doing approximation comes into play. So this 1.6 goes as 1.6 into 1, and this is approximately 1.6 into 4, which is 6.4. So I can approximately write 4 over here. Now let us understand that 2 into 9.1 is 18.2, and 6.63 into 3 is, let's say 19.9, let us say. But like this is 18.2, this is present over here, and I can approximately write this as 1 upon 3 approximately, because you understand that these options A, B, C, D are pretty far apart, they are not very close. So this order of approximation should work. So let us see what we get. So this is 4 by 3, and then okay, so this thing is now gone. So we are now left with essentially this is equal to 4 upon 3 into 56.25. Alright, so this is into 10 raised to 3, of course. Okay, so 56.25 into 3 is approximately 168.75. It's exactly 168.75, but I am going to write down that value as 168. The reason being I want to divide by 2. So this is 168 into 10 raised to 3. So if I divide over here, I get 1, and okay, if I divide by 2 over here, I get 2, and here I get 84. And if I divide this again one more time, then here I get 42. Okay, so we know that 10 raised to 3 divided by 40, so this is approximately 100 divided by 4. So this is approximately equal to 25. This is the best possible approximation. And please note that there are, so we know that this is in kilo electron volts. Also please note that there are no values close to 25. So we can safely say that this is going to give us the correct answer. Alright, so this was a lengthy method wherein we had to approximate appropriately. The physics based part of this particular question was pretty small, and the mathematics was slightly complicated. Now in modern physics, as we study modern physics, there are some certain relations and formulae. If we do remember those relations and formulae, it really helps in order to simplify things a lot. So one such relation is the relation between the wavelength lambda and the accelerating potential V of the electrons. Let us say an electron is accelerated through a potential of V, okay, through a potential difference V. Then this particular electron, after acceleration, achieves a certain particular wavelength. Okay, that particular wavelength is lambda. Then the relation between the electron's wavelength and the accelerating voltage will be given as E times, so E times V. This is the energy, this is going to be equal to P square upon 2m. So this is going to be equal to h upon lambda the whole square divided by 2m. So this particular equation can give us, see, E is known, the charge of electron 1.6 into 10 raised to minus 19 coulombs. The mass of the electron is known, 9.1 into 10 raised to minus 31. Planck's constant is known, the constant 2 is a constant. So this actually gives us the relation between lambda and the accelerating voltage. So if, as students of physics, we do know this relation, it happens to be approximately lambda is equal to approximately 150 divided by V. Now this particular kind of relation pops up again and again, the relation between the wavelength of the electron that has been accelerated by a potential difference of V, because this energy is now in electron volts, because one electron has been accelerated by a potential difference of V volts. So the interconversion between joules and electron volts is also bypassed or skipped in this particular analogy. So here lambda can be simply substituted and we can just write down the value of lambda, which has been given 7.5 into 10 raised to minus 12. So that is going to be equal to under root 150 divided by V. So this is easy to find. Under root of 150 is relatively easy to find because this is going to be 25 into 6. Under root 25 under root 6. Okay. So this we can find out. Therefore, in this particular method, we get V to be approximately, squaring both sides actually, we get V to be equal to 80 into 10 raised to 3 divided by 3. Okay, that is in volts. Okay, so this is what we get. And if we have to write this down in electron volts, so the closest value to 80 by 3, 75 by 3 we know is 25. So the closest value out of the 4 options given is going to be equal to 25 kilo electron volts. Okay, so this is the accelerating potential through which this electron has been accelerated. So how much energy will it have? It will have EV, electron volts of energy. E into V is the value, and this electron volts of energy, this electron volts is the unit. So this much amount of energy will be present. So if we do know this relation, this particular question becomes pretty simplified. If we know this relation, lambda is approximately equal to under root of 150 upon V. I do recommend that the student should know this particular relation by heart in order to solve such questions simply without having to do a lot of calculations.